Hi, this is Professor Fernandez. We are talking about class notes F in lesson 4. So I've pre-written out a few things here just because it's easier to keep them in mind rather than writing them out. The first thing I want to mention is that what's happening in this class notes, well, we are considering the second case of solving Cauchy-Schulz constant coefficient second order linear differential equations. This is the case where when you write out the characteristic equation, you get a real repeated root. So if you just follow the recipe we've been following so far, which is you write out the ODE solution by e to the root times t, that would give you two solutions that are exactly the same. That is a little bit of a problem because on our based on everything we've done in the ODE theory part of the course, the Wronskian of these two solutions is 0. So that means that they do not form a fundamental set of solutions, and we cannot therefore use them to write out the general solution. So it's not to mean that we discard them completely. They are solutions, they just don't form a fundamental set. So we can't write the general solution as a linear combination of those two. But really, it's because we're trying to do too much, right? It is the same function, just copied again. So what we're going to do is retain one of these functions, and we're going to try to construct a different solution, a second solution, y2, from y1, using a particular method. The more general method I mentioned here is called reduction of order. You can read about that in the additional reading that I suggest at the end of the lesson. I am just in this class notes going to kind of give you some very general overview of how that general method is applied to this particular case. So a few things we could say here, right? So y2 equals y1 doesn't work out because it gives us a 0 Wronskian. So you might think, okay, how about maybe some multiple of y1? How about if y2 is, some number times y1? Would that be a good enough second solution? Would I get a fundamental set then? The answer is no. So if y2 is a constant multiple of y1, we again get a 0 Wronskian. So I encourage you to check that to make sure that you understand how all these things are working, right? So this is the claim that the Wronskian of y1 and k times y1 equals 0, no matter what the value of k is. So in other words, this slight generalization of trying to get y2 to be some relation in some relation to y1 is also not working out for us. So the next thing that you might think of trying is, okay, maybe not a constant function. What if I make y2 some unknown function, v of t, times y1? Okay, that sort of beefs up the generality. And this turns out to actually work. You have to make lots of choices, and you have to do lots of algebra and simplification along the way. So that's what I say here. So let's try a second solution that's a not constant function, in this case v of t, multiplied by y1. What did I do here? I wrote out the e to the rt, right? This used to be e to the r1t. And I just wrote out what R1 is in this particular case. Here it is up here. The root, right, when the characteristic equation has real repeated roots, is negative b over 2a. And that comes from the quadratic equation. So I've written that down here for the y, for the second solution. And what do you do now? So at this point, you would take this y of t and you would substitute it into this original Cauchy-Schulz. And you would use the fact that this function already solves the Cauchy-Schulz. And after a lot of algebra, so I recommend the reading in the textbook for the additional details. After a lot of algebra, you get a very, very simple condition, which is a v double prime equals 0. So again, you might be wondering, how does this help? Well, remember that we posited this new function, this new solution, as an unknown function times something we already knew. So this condition helps us solve for that unknown function. If the second derivative of something is 0, and again, a is non-zero because a is the leading coefficient of this. If it were 0, then we wouldn't be dealing with a Schulz. We'd be dealing with a first order ODE, which we did lots of in the first unit of the course. So anyway, so since a is non-zero, we can divide through, and we have v double prime equals 0. So you integrate once, v prime equals some number. You integrate again, v of t equals some number times t plus some other number. And that gets you to this v function. Great. So at this point, what the math is telling you is that you have a lot of freedom in what's going on. But some of that freedom is deceptive. Suppose that k1 is 0, okay? So that v of t equals k2. Well, then if you go back up here, then what you're doing is you're doing these, second solution is becoming a constant times the first solution, right? But we said that that doesn't work up here. Okay, so we cannot have k1 equal to 0. But you can have k2 equal to 0. That turns out not to matter. And again, that's something that you should check just to make sure everything we're doing here is making sense. So it also turns out that you can choose any k value you want, right? Why? Because whatever k value you choose is going to end up multiplying a solution you already know. And when you put the y in here and differentiate it again, that k value that you chose is going to show up here, here, and here. So what can you do? You can factor it out and divide. Okay, so that's another clue that tells you that it doesn't matter which k value you choose, as long as you don't choose k1, sorry, as long as you don't choose k1 equals 0. Because then you're left with v of t equals k2, right? And that we said is an issue. So that justifies this statement here. We can choose k1 equals 1 and k2 equals 0 without loss of generality, so that this is 1 and this is not there, so that v of t equals t. Okay, and then we take that, we plop it in there, and that yields this as our second solution. And in one of the practice problems, I ask you to show that this solution and this solution do indeed form a fundamental set of solutions, right? So that the takeaway from here, I'll scroll down a little bit, I put here in the recap, is that when the CC sol that you're looking at, when its characteristic equation has real and distinct roots, right? Two different real roots, let's say like -5 and -2, then the general solution looks like that. But like we just saw, if it has real and repeated roots, like -1 and -1, then you have the usual e to the rt, but then the second solution is t times that e to the rt. Okay, so that's effectively what we've shown.